Hi there, we're about to do an example of calculating truss forces of a simple truss. This method we're going to use is called the method of joints, and it only works for trusses that are statically determinate, meaning it follows that formula on the screen. Double the joints is equal to the members plus the reaction forces. If your truss doesn't satisfy that equation, then the static equilibrium equations that we're going to use are not enough to determine the reactions inside your structure. There's just too many unknowns. Note that we're making some assumptions when using this method and the work we're going to do. We are assuming that all of our members are perfectly straight, that the loads are applied at the joints, our joints are pinned and frictionless, each member has no weight, and members can only experience tension or compression. All right, here we go. Here is our truss problem, which you may need to hit pause and copy stuff down. But I've got a truss, I have a load, I have my reaction forces labeled based on a pin support and a roller support. I have drawn the joints and illustrated kind of where the members are going, intentionally leaving some space for me to fill in the answers of the truss forces that I find as I solve. And the first thing we are going to do is we're going to use the lengths that have been provided to find angle measures. Okay, so you can assume it's intended that AEDB is a rectangle and BDC is a right triangle. You can see AE is being 3 is 3, so this is 3 as well. That's 4. I'm basically gonna have to do a little bit of trig. So if you think of writing out this triangle right here, which would be EED with sides of 3 and 6, and let me just kind of mark an angle right there relative to this angle at D, which would be angle ADE. That's the opposite leg, this is the adjacent leg. I would be able to use the tangent ratio to say tangent of, let me just call it theta, is equal to the opposite over the adjacent. And then theta is the inverse tangent of 3/6, which is where I need my calculator. Excuse me. Okay, so on this calculator at least, if I put 0.5 on my screen, maybe. Then I'm going to take the inverse. So I'm going to go trig, inverse tangent, and I get an angle of 26.56. I'm going to round that to the nearest tenth. So 26.6 degrees. So I'm going to fill in what I know here. That's 26.6 degrees. The alternate interior angle is also 26.6 degrees because BD is perpendicular to the base here. These two have to add up to equal 90. So I'm going to have 63.4 and 63.4 over here. Another alternate interior angle. And I've got all these little cute angles now I want to turn to triangle BDC, which is a 3, 4, 5 right triangle. I don't really need the hypotenuse length, I just needed to get an angle measure either this one or this one is fine, so let me just kind of mark that one, and let's call it beta for a second, and let's use tangent again. Let's say that's the opposite leg and the adjacent leg relative to that, so we'll say tangent of beta is equal to 3/4. So then we're going to have the inverse tangent of 3/4 to get that angle. So bringing my calculator back over, I'm going to have 0.75 on the screen, and then I'm going to use the inverse tangent of the 0.75, and rounding this is 36.9. Excuse me for my dog in the background. So this is going to be 53.1 degrees up there at vertex B with a complement. Okay, so that was the first step, is knowing the angles. The second step is going to be to find the reaction forces. At the supports. And we're going to do this using the static equilibrium equations. The first one, though, is we're going to say the sum of all the moments is equal to 0. Now, the moments, okay, a moment is a turning effect, right? Remember what a moment is? It's turning. So where's our fulcrum? Our fulcrum is at the pinned support. All right, so we've got that pinned support, and we're looking for any force that's acting on this truss that's not at the fulcrum. If you push or pull right at the fulcrum, you're not going to create a turning effect. You have to have some distance away. And so the two forces that we're identifying as forces that would create a turning effect is the load, that's some distance away, that's 200, and then this reaction force over at C in the y direction. Hopefully understand the labeling method here. R for reaction, and then subscript label, I've got a C because it's at location or at vertex C, and then Y because it's vertical. Okay, so the distances here, let's see, this was 6 and that was 4, so this is 10 all the way there to the fulcrum. So the two distances that really matter are the 6 and the 10. So we've got one moment is caused by the load, the 200 times the 6 units. Okay, that's a moment, and that moment is clockwise. Clockwise happens to be a negative direction. Just kind of think of that product as a moment, and it's negative because it's clockwise. And then we know this reaction force is going to be keeping this kind of static, so it's got to be going in the opposite direction. We just don't know how big it is, but we know its distance is 10. And then if it's counterclockwise, that would be a positive direction. So these two moments have to add, okay, right here, add to equal 0. That's our static equilibrium equation. Why does it have to equal 0? Because our truss we expect to be sitting still, to not be spinning. So if it's still and it's stationary and it's not beginning to turn in one direction or the other, then these things have to be balanced. Okay, I have one unknown, so we're going to solve this for the unknown. And then I've got one of my reaction forces. So right here we have a negative 1200 plus, this is 10 times RCY. I'm going to add 1200 to both sides. I'm going to divide both sides by 10. And I've got the reaction force at C in the y direction. This right now is 120. And that's really a positive 120, vertically speaking, because it's up. This 200 is actually a negative 200 because it's down, if we're thinking vertically. All right, and then the next equation that we're going to use is going to say that the sum of all the forces acting on this truss in the y direction, they have to add up to equal 0, because it's got to be balanced. Our bridge is not getting pulled down, it's not beginning to float up in the air. So we need to identify where they're at. Well, we have a reaction force at E in the y direction. We have a load. We have a reaction force at C in the y direction. Those are all our vertical forces. Here, here, and here. They all have to add up to equal 0. Okay. The load we know is a negative 200. The reaction force at C we know is a positive 120. The reaction force at E in the y direction, we actually kind of know from looking at that it's going to have to be up. I got 200 down, I'm going to need a total of 200 up, and I've only got 120 up so far. So I kind of know it's going to be positive. And I'm going to combine like terms right there. So I get a reaction force at E in the y direction, and that's minus 80 is equal to 0. Add 80 to both sides. And we found out that that is 80 units up. All right, and lastly, the sum of all the forces that are horizontal, they also have to be balanced. Well, I have a load that's down, that's not horizontal. I have no forces, no wind force or anything that's pushing or pulling on the bridge. I do have the pin support that's reacting or ready to react. That's the only one. So that reaction force at E, that's horizontal, is the only horizontal force. So there's nothing else to say plus anything else to make it 0. It's just that one by itself is 0. Okay. So we've now finished finding all the reaction forces. We're now going to find the internal members joint by joint. Okay, I may have to scroll this up a little bit. I would suggest trying to start at the pin support, where you have a horizontal and a vertical node force. So I'm going to write joint E. And I'm going to draw a free body diagram. I'm going to leave a little space below there. This dot is E. And I'm going to draw the members and the reaction forces. Alright, so AE. Now here's one thing. This is the first one we're doing. When we do this method of joints, we assume that the members are in tension. I don't know how much force is going through them, but a tension force is a pulling force. It's pulling on the joint. So I'm going to draw that arrow tip away from the joint for AE and ED as well. Now I actually don't know if they're in tension or not, but I'm assuming. Okay. I'm going to say that open arrow tips are assumed and closed arrow tips are known. That's just for me to have a graphical way to keep track of this as I'm solving. You'll see how this works out. All right. So also at joint E, I know I have 80 units of upward force, and I know I have 0 units of reaction force horizontally. Okay, so at the joints, we don't have the need for a moment. We only need to satisfy static equilibrium horizontally and vertically. So at each joint, we're going to say the sum of all the forces that are vertical and horizontal. It doesn't really matter which one you do first. other than sometimes at a specific joint you have the ability to solve for one and not the other right away. In this case it really doesn't matter. So I'd say the sum of all the horizontal forces has to equal 0. Identifying those, it'd be the reaction force here, that's 0. The other one would be ED, or DE. I try to keep it in alphabetical order really, even though I wrote it here. So try to write it in alphabetical order. Okay, now we have to keep the signs of these, even though we don't know and they're assumed. We have to keep the sign of this consistent with the direction we drew the arrow. Okay, so right is a positive direction, up is a positive direction. So in both of these cases, we're going to leave this as a positive. But down and left are negative, we would have put a negative into the equation. So I'm assuming it's positive, which means, or I'm assuming it's tension, which is right. Right is positive. So that way the assumption's kind of built in here. Okay, in this one it really doesn't matter. We end up finding that DE is 0. It's kind of neither tension nor compression. So all the way up here, I'm going to go ahead and put a 0 here. Now I'm going to say the sum of all the forces in the y direction, they have to add up to equal 0. Okay, so that's the 80, which is up, which is positive, and then AE is assumed to be in tension, which is up. Up would be positive, so I'm just kind of clarifying. I'm assuming that's positive. And then I solve. I'm going to subtract 80 from both sides, and I'm going to get a negative 80. Alright, what happens here is, with this idea of assuming a member is in tension and solving, if you ever get a negative value, what you're finding is the opposite of what you assumed. Okay, remember we assumed tension. We set up our equation, okay, based on that. The magnitude of 80 is correct. Okay, but what's different is that it's the opposite direction. So the negative is not about magnitude as much as just the direction is the opposite direction. So that tells us our assumption was wrong. So, therefore, compression. So I have 80 with a little c for compression. And I'm going to go ahead and put 80 here as my reaction force and 0 here. And I should put the 120 here. Forgive my cough. I've had a cough for over 10 days now, and I can't shake it. It's not ideal time to be making a video, but it is what it is. Okay. We found everything we can find at joint E. Right? We know this is 0. We know that's 80, the magnitudes. There's no other unknowns. So we're ready to move on to another joint. I can, I guess, kind of trace out a little bit quickly for you to kind of understand maybe what would happen if we go to another joint. It might make sense to go to D. We now know that ED is 0. And we know this load is 200. So we do have one vertical and one horizontal. But when we set up our static equilibrium equations, you're going to want to have all but one in a certain direction. And you have a diagonal at D, this AD member. And you need to know that a diagonal is going to create, we're going to break it down into two different vectors or forces. We call them component vectors. A diagonal is going to have a horizontal component and a vertical component to it. So at D, you kind of have to look horizontally. We've got one here, DE. We also have DC, we have 2, which is unknown. And we've got the diagonal, 3. And you only know one of them. So you know one out of the 3, you're going to have trouble solving for the other one. Vertically, you have a known at the 200. We have BD as unknown. And the diagonal, that's unknown, the vertical component of it. So again, you're going to have 3 vectors that need to add up to equal 0, and you only have one of them. And so both equations are going to have us stuck with trying to want to get something out of one of them, and we're not going to be able to get anything. Okay, so D is not going to be good. If we go up to A, we have this known vertical. We don't have a known horizontal. However, vertically, there's no other exactly explicit vertical members, just the diagonal. So the diagonal has the vertical component in it. So that vertical component is the only thing that can balance the 80 of compression. By us knowing that vertical component, we're going to be able to kind of use trig and a right triangle and figure out the horizontal component. Once we know how much horizontal force is here, we'll know AB, how much it has to have to balance the horizontal component. So let's go ahead and go to joint A. I'm going to go ahead and kind of use a separate sheet of paper, kind of cover some of this and keep it a little closer to what you've got up here. But you guys would be working this out in your notebooks. Let me get another couple sheets just so it doesn't bleed through as much for you. Kind of distracted by what's underneath. Alright, so the next thing we're going to do is go to joint A. And at joint A, let's see, I've got 80 compression. Compression is a pushing force on the joint, and this is known, so I'm going to do a closed arrow as a reminder to myself that I know this. This is 80. It's positive. I have AD, which is assumed to be in tension. And then I have AB also will be assumed to be in tension. Okay. So AD is going to be broken into, though, component vectors, we said. You're going to have a horizontal and a vertical. You kind of go, I didn't mean to close that, but kind of head to toe here with the arrows. Start at the joint, and you can do a horizontal, and then to match the length of the diagonal, and when you get to the same horizontal distance, then turn vertical and have that arrow extend from there. You should form a right triangle. And then these are going to be labeled AD sub X and AD sub Y. So if we think about, doesn't really matter where I put it, but my static equilibrium equations, and just identifying where are the vertical forces, where are the horizontal forces. Okay, vertically I have the 80, which I know is positive, and I have the diagonal, which has ADY, which I don't actually know if it's down, but I assume it is. Okay, right? I'm assuming that it's tension. Tension, if AD was in tension, it would be going this direction, which is down and right. So down is a negative direction, and those will have to add up to equal 0. And then on the x's, you would have AB, unknown if it's positive or negative. We just are assuming it's to the right, which is positive, so that is assumed. And then ADX right there, okay, if AD is in tension, that's, we said down and right, or right and down, that would be right again, which is positive. So we're kind of assuming both of those. They can't both be to the right, so one of them's going to have to be the opposite direction. Okay, so there's kind of identifying our two vertical forces, our two horizontal forces. The equation you can start with is the one where you already had a known and you only have one unknown left. If you only have one unknown, you can solve for it, right? So if we left the variable on this side, we'd end up with a negative ADY equals a negative 80. We would have subtracted 80, but we don't want a negative variable, so we'd multiply through by a negative 1, right? And we would get that ADY is equal to positive 80. The fact that our answer worked out to be positive means it agrees with our assumption of tension. So AD is in tension. Now we don't know what AD is, we know what ADY is. Okay? We actually want to know AD. So let's draw, just so it's a little off to the side from all that, let's draw this right triangle, which was formed by AD, ADX, and ADY. And we just found out that ADY right here, we just found out that it is 80. Now we're going to use that force as a distance and use trig. So force is a vector, and the magnitude should follow the directional relationships, just like distances do. Okay, this angle right here is actually known. If you come back up here, remember we found that to be 26.6. So let's get this actual member of the truss, AD. That is the hypotenuse of this right triangle, and AD is the opposite leg relative to that 26.6. Sine is the ratio that uses the opposite leg in the hypotenuse. So we're going to say sine of 26.6 is equal to the opposite leg, which is 80, divided by the hypotenuse, which is the unknown, AD. Okay, I'm going to multiply both sides by AD, all right, and then I'm going to really divide both sides by the sine of 26.6, so that AD is alone. So that's what I need to solve on my calculator. Yeah, maybe it's easier for me to pull up a graphing calculator. With a graphing calculator or any calculator using trig, make sure you are in degrees. I'm going to check my mode. You can see I'm in degrees right there. Okay. So I just need to do 80 divided by the sine of 26.6. And I get 178 point, I'm going to round that to 7. So 178.7 units of force of magnitude. So that's an actual member. Let's kind of write that down here. 178.7. And I don't know, I've been using red, I guess, up here. Let's fill that in here. 178.7, and we knew that was in tension, so I'm going to do a little T underneath that. Okay. All right. Now, if I go back to this joint and say, oh, hey, all the horizontal forces have to add up to equal 0, I actually still have two unknowns. I don't know AB, and this is not AD, this is ADX. It's the horizontal component, and I first found the vertical component. I now have the hypotenuse, but I actually never found the horizontal component. So I want to find the horizontal component. So I want to find ADX so I can plug it in here and then get AB. And I'll have another member. Now how to get this horizontal component? It's just coming back to the right triangle. I can use trig again, or now that I have 2 out of 3 sides, I've got this side is 80, this side is 178.7. I could use the Pythagorean theorem. That works too. Just treat the forces like distances in solving your right triangle trig. It really doesn't matter. I'm going to go ahead and, because that's a rounded answer, I'm just going to go ahead and use trig again. I'm going to say relative to that 26.6, I mean really that angle is rounded too, right? But I'll say tangent of 26.6 is equal to the opposite over the adjacent, the opposite being 80 and the adjacent being the horizontal component, ADX. Okay, just like we did here, the variables in the denominator, we're going to really multiply both sides by ADX so that ADX is on the other side of the equal sign in the numerator. Then we're going to divide both sides by the tangent, so the tangent, or that trig ratio, is going to end up in the denominator of the opposite side. It's really just a property of proportions. Okay, so we're going to pull out our calculator, and we're going to see what is 80 divided by the tangent of 26.6. And I get 159.8. Okay, so that gets to go here. Now remember, we found out that AD was in tension, right? When we found ADY. So that means we know that AD's arrow was down and right, which means the down is confirmed, and it means the right is confirmed. So we actually know that that is positive. That is a known tension. Tension puts this right. Right is positive. So this is not assumed. The AB is assumed. So we have AB plus 159.8. Those have to add up to equal 0. We're going to subtract 159 from both sides. And the negative, the opposite value, tells us our direction was wrong. We've got the magnitude, but the direction. So that tells us AB is in compression. Okay? So AB is 159.8. It's compression. So horizontally speaking, at joint A, we had AB, and there's no other horizontal, it's just this diagonal. So you can see the diagonal, though, has a horizontal component. So the horizontal component here is pulling on A, and then AB is pushing on A, both from the right. So one's pulling A to the right, and then this is pushing A back to the left, because it's pushing from the right, so it's pushing that way. So they'll balance each other, right? The magnitudes are different because this one's diagonal. So diagonally the force is bigger, but its horizontal component is equivalent to 159.8. Okay, that's what we just figured out over here. Okay. So now that we got AD, we do have more. Excuse me, to come back to joint D. And not only do we have AD, we already have ADX and ADY. So, you know, we could go to joint D and label all of that. Actually might work out just fine. There's more than one way to do this. You know, you don't have to go to joint D next. I could have gone to joint C, used the 120. You know, I think we got 3 joints left, B, D, and C, and we should only have to visit 2 of the 3 before we have everything filled in as being known. So let's go to joint D. And at joint D, I have a 200 down, right? I have DE 0. I have CD unknown. Can label that. I have BD, drawing the arrow up because it's unknown, so assuming tension. And then I've got the diagonal, which we found to be in tension. Which means I actually know this is from AD's perspective, or from joint D's perspective. I know I have ADY going up, and then I have ADX going to the left. And we actually have those numbers, right? ADY was 80. ADX was 159.8, which here in this case left is negative. So if we write out the sum of all our forces that are horizontal, have to add up to equal 0. Let's see, horizontally we have DE, which is 0. We have CD, assumed tension, which means assumed right, which is assumed positive. And then ADX, which is known to be left. Okay? And we know that it is, so negative left 159.8. So solving this, 0 plus CD is just CD. We're going to add 159.8 to both sides. And there you go. And it worked out to be a positive value, which means our assumption is correct, which is tension. So we're going to come back up here and fill in CD as 159.8 with a T underneath for tension. All right. Now vertically, we'll say the sum of all the forces that are vertical, they have to add up to equal 0. So they are the load, the diagonal AD has the vertical component, and BD. BD is assumed to be tension, which is up, and up is positive. ADY is known to be positive, that one's known. The load is known to be down, that's negative, known. Okay, so these 3 values have to add with each other to make 0. So the load is 200. ADY is 80. I'm so sorry for my dog in the background. Negative 200 plus 80 is negative 120. He barks at any single thing he sees out the window. He just barks. He's not a very smart dog. We're going to add 120 to both sides, and we get a positive 120, which means our assumption that BD was in tension was correct. Tension's a pulling force, right? So then you get the 200 kind of, if you will, pulling down. You get the 120 kind of pulling back up this way, but that's not enough to balance out the 200. It's the diagonal here that's also, right, that 178.7 of diagonal tension force is providing 80 units of upward force. So the 80 units of upward force built into AD and the 120 make our 200 units of upward force to balance that 200 units of downward force. Okay? We have one last unknown. If you're kind of keeping track of them, filling in these blanks, BC is the only unknown. It doesn't matter if you go to B or to C. I think it's going to work out to be the same. You have a horizontal and a vertical, and then the unknown diagonal. Here, horizontal, vertical, unknown diagonal. Numbers are the same. Okay? So, really doesn't matter. Let's go ahead and, I don't know, let's just go to the support, the C, and draw that. So at C, we had a known 120 units of upward force. At CD, which we just found to be in tension, so that's away, we got the 159.8, and then we've got the diagonal BC, which we're going to assume tension again, right? Now that's the diagonal, so we're going to have to break it into a vertical and a horizontal component. So I've got BCY and BCX. Alright, and the way I drew those, I don't actually have the angle. You know, if you're focusing on that triangle, the angle we found quite a while ago, right here, that 36.9 degrees. Okay, that's actually right here, right? Which is alternate interior to this. So if I want to just draw that triangle for myself, that's 36.9 with BCY, BCX, and BC is the hypotenuse. Alright, my goal is to get the hypotenuse. It doesn't matter which leg I get. If I can get one of the two legs, I can then use trig. I've got this 120 up, right? That's vertical. So what if we say the sum of the forces that is vertical, they have to add up to equal 0. So that's the 120 for sure going up, plus BCY, assumed to be in tension, which is up and left. Up is positive, so assuming positive, those have to add up to equal 0. I subtract 120 from both sides, and I get a negative 120. The magnitude's correct. The negative tells me compression. So that is 120, and BC is actually going this way. It's not up and left, it is down and right. Okay. Now, this side, relative to that angle, that 36.9 degree angle, this is the opposite leg. BC is the hypotenuse. The trig ratio that uses opposite and hypotenuse is sine. This is the last thing. I'm going to do the sine of 36.9 is equal to the opposite, which is 120, divided by the hypotenuse, which is the member BC, now known to be in compression. Okay, and I'm going to use that property of a proportion that really these two, they're just going to trade spots. Multiplying both sides by BC is an algebraic step that gets BC to the numerator over here. And then dividing both sides by the sine of 36.9 degrees. And all I need to do is type that into my calculator and I have the answer. So let's see, 120 divided by, you see the screen? Doesn't show up on the .cam grade, does it here? The sine of 36.9. I've got 199.9. It's at 86, but I'm around it, so 199.9 of compression. So right here, I'm going to fill in 199.9. And there you have it. We have calculated all of the forces with this truss. All of the internal forces, the reaction forces, right, at the roller support and at the pin support. We had the load given to us. We found all the angles. We did it. All right. Good job.